Alright, let's look at all the forms of mechanical energy. Remember, mechanical energy is just the total of all the kinetic potential energies that you have in an object or a system of objects. So it could be all the stuff added together that's going on in the room. But we're going to focus just on one object at a time, typically here. First kind of energy we're talking about is kinetic energy. That's due to motion. So say we have a baseball flying along off to the right side here. It has kinetic energy because it's moving. The potential energy is the stored energy. So the stored energy in that baseball. We've already talked about gravitational potential energy. That's due to position above the ground. So let's say that ball is flying above the ground, heading towards someone ready to catch that ball. Right? It has kinetic energy because it's moving, and it also has gravitational potential energy because it is some height above the ground. The third kind of mechanical energy we're going to talk about is a potential energy as well. It is an elastic potential energy, and it's due to the deforming of an object or the stretching of something. Something like a spring or a rubber band, when you compress it or stretch it, will have some elastic potential energy. So maybe this ball was attached to a wall with a bungee cord, and between the ball and the wall there, as the bungee cord stretches out, it's going to have some elastic potential energy stored in. Eventually it'll pull the ball back because of that. That energy will cause some change there. So what this does for our total energy then is we look at the total energy to be the kinetic energy plus the gravitational potential energy plus the elastic potential energy. So as we look at the whole system, we'll look at all three of these forms of energy specifically within the object or the system that we are dealing with. So let's look at more details of the elastic potential energy of springs. Hooke's law tells us the force required to stretch or compress a spring follows the form of K, which is a spring constant, times delta X. So let's see, if we just have a spring over here and we have a little block attached to it there, the delta X is the displacement of the spring from the equilibrium position. The equilibrium position is this green line here, which just shows where the spring would be normally if nothing was being done to it, nothing being compressed, nothing being stretched. It's just sitting there on the table, for example. If we were then to apply a force to it, say off to the right here, and stretch that spring out some, we would then have a displacement, or delta X, the difference between where it was at equilibrium and where it is now as we pulled with a force applied to it. The K, as I mentioned a moment ago, is the spring constant. This is measured in newtons per meter. Basically measures how stiff the spring is or how loose the spring is, maybe how slinky it is. A smaller spring, a thinner spring would have a lower spring constant. A very thick spring, like you have on a car, a coil spring, would be a very high spring constant. Alright, so we want to look specifically then at the stored energy that is in the spring. We use Hooke's law to find the strength of the spring. So we'll actually look at an experiment which simply shows some consecutive events that have taken place. We have a spring that has just have a little load hanging on it, and each of the consecutive loads is a little bit heavier than the previous one. And so as a result, you get a greater and greater displacement. So from here down, right, we have a displacement acting on the spring here. Right, this would be delta Y in this case, since it's vertical. We have our displacement, we have our force that's being applied to it here as we look at that particular situation. Now if we graph the data that comes from that experiment, we'll get something that looks similar to this. You get a nice linear relationship between the applied force and the displacement until you reach the point where the metal of the spring itself actually starts to permanently deform and get stretched out of shape. And so we see this nice linear relationship here. So if we look at the actual area under the curve that's shaded here and look at the fact that it's simply multiplying the force times the displacement, all right, we have the 1/2 the base times the height for the triangle that we're looking at, and the force itself, remember from Hooke's law, is K times the displacement, and so that then goes back right up in here, and that's where we get the 1/2 kxx, and just put those together, and so you get the work that's done to the spring is 1/2 the spring constant times the displacement squared. So we put this into the potential elastic form, where the elastic potential energy is 1/2 the spring constant times the displacement squared. And yes, your answer should be in joules. So let's look at an example of elastic potential energy. We go back to our original spring, and we've had a displacement of 0.8 meters and a force of 20 newtons applied to it in order to make it displace that. So first we need to find the spring constant. So we put in the 20 newtons equals the spring constant times 0.8 meters. We need to divide out the 0.8 meters from each side so that we get the spring constant by itself. That leaves us with a spring constant of about 25 newtons per meter. So it says for every 25 newtons we apply to that spring, it should stretch 1 meter or be compressed 1 meter. So now we can put that spring constant down into the elastic potential energy equation. So we put in the 25 newton per meter times 0.8 meters squared. I highly recommend that you put that 0.8 meters in parentheses and square that. So it reminds you you're squaring everything in there, including the units. And then if you work all of the numbers out there, you end up getting about 8 newtons times meters. So since this meter here was squared, you ended up with newtons over meters times meters squared, and one of those meters cancels out, leaving you with Newton meters. And that works out to an elastic potential energy of about 8 joules. So that'll do it for the elastic potential energy, and use this to help you work out the practice problems on the worksheet.